the key system design parameters: performance, resilience, and power consumption. Oftentimes, when we talk about resilience, we are basically saying, "Oh, the sky is falling. The sky is falling. Systems will be failing all over the place," and things like that. That's not exactly the case. The case is that we basically have to deal with every time we run into problems with our resilience, we need to compensate for that. We need to compensate in terms of adding maybe more hardware or dealing differently with it in software. And that may actually cost more money to do that, more power, or just, takes longer to do, so it actually costs performance. So it's actually an optimization problem. And the challenge here is to basically build a reliable system within a certain given cost budget. After all, we won't be given billions of dollars to basically build an exascale system or post-exascale system. This requires us to fully understand what's going on in these systems in terms of what is the fault model, what is the impact of faults on applications, and how can we mitigate against hardware and software errors, and how can hardware and software help in this. So the objectives of this particular project is to identify, categorize, and model the faults, errors, and failures in HPC systems within the US Department of Energy, and to develop a fault taxonomy, a catalog, and models that capture the observed conditions and then also the inferred conditions in current systems, and then extrapolate that knowledge to exascale systems and beyond. This project basically provides a clear picture of the fault characteristics in current DOE computing environments. It improves resilience through a reliable fault detection at an early stage and actionable information for efficient mitigation. So the way this project works is actually, initially we started working on sort of offline analysis, looking at the data that we're getting from the systems, analyzing the data, categorizing the data, creating a fault catalog and models. Then we started looking at application sensitivity and studies and error propagation studies, doing application models, and feeding that back into the catalog. Right now we're in the stage of online fault detection and categorization, where we look at live data from the system and try to identify the health of the system in real time. And all of this is done while refining instrumentation points, while we're trying to figure out what information do we actually need from the system, what information we can just throw away. So in the beginning of this project, about 4 years ago, we started developing a HPC fault taxonomy. This is already based on earlier work. There has been a significant amount of work at other labs. There was a workshop organized by Mark Sneer a few years ago, where we basically sat down for a week to discuss the HPC fault taxonomy. And based on that, we came up with a common set of terms, metrics, and methods. And I just made that more clarified that a little bit more, and basically came up with all these different terms. And for example, a fault, right? A fault is typically the root cause. It's not necessarily something you actually see. That's the problem we're often facing, that faults we often can't see. They can be benign, dominant, they can be active, things like that. And a fault then at some point produces an error. An error is typically something we see. We may not see it. There's maybe detected and undetected errors, right? There may be mask errors. There are hard and soft errors. And then there, of course, is the failure. Failure is actually when a service fails, or when, for instance, when you have a library and at that library interface a certain function doesn't work anymore, right? That's clearly a failure. And there we have also detected and undetected and permanent and transit and so on. And of course the worst case scenario the safety errors. So when we developed this fault taxonomy, we started looking at the various different systems we have at these 3 labs, and started analyzing these systems in terms of what information do we see in the system logs, and what can we make out of that. So at Oak Ridge, we analyzed 5 different generations of supercomputers over a period of 8 years, which is a total of something like 1.2 billion node hours of system logs. We combined this information from different lib system logs, and we started using standard methods, and also created new methods for temporal and spatial analysis of errors and failures in these systems. And sort of we analyzed the correlation between different failure types, and we also compared the mean time between failures of these 5 systems. And something interesting to see here is that the mean time between failure here is normalized on a per node basis, basically. It's scale normalized. And we can see that the mean time between failure actually sometimes jumps rather drastically, basically on almost all systems except for this one. And this is something that actually was relatively new. We didn't expect that to happen, that even over time systems become more unreliable. And initially we thought maybe this is sort of a bathtub curve thing, that the system is becoming unreliable because it's becoming old. But here the system isn't really old, and here the system isn't really old either. So this is something completely different. This is typically changes in the system itself, where we updated maybe the software, or changes in how we use the system. Maybe we run applications that actually run the system more service, and therefore cause more error. All these different types of errors and failures we're seeing in different percentiles of their contribution to the overall failures, and we can see that between different systems sometimes there are similarities, but oftentimes they are not. We see on different systems also different errors and failures, despite the fact that all of these systems here are actually all Cray systems. They all come from the same vendor with a similar software stack, just the next generation. They all have the next generation hardware from the previous generation. And we also always see that things like ECC errors, ECC double bit errors, and things like that, yeah, they're there, but oftentimes we have network errors, and network errors are very typical to that particular network generation, because oftentimes we just report them back to a vendor, and the vendor then fixes that in the next generation. But then the next generation, then we see different network errors, right? So in one particular network we may see drop packets. And the next one, we don't see that anymore. But we may see some node lockups that suddenly disable routes, network routes, right? So then we started looking at, okay, how is the mean time between failures distributed, and also how the failures distributed, and how are that distribution related to the mean time between failures. And up here we can see that the red one is the mean time between failures, and the failures are nowhere near that, right? So the mean time between failures is, just that mean. The distribution is much, much different, right? So, and the spatial distribution sometimes really looks odd. We sometimes see correlation between heat, and so Titan was the first system where we actually saw a correlation between heat and failures. Previous systems did not have that at all. And in terms of mapping the failure distributions to actual statistical distributions, you can see that Weibull actually matches typically pretty well. So we learned a lot of lessons from this. I don't have to go through all of these. The most important one is actually that mean time between failures over average over time is not a very good measure for reliability. We need to come up with something different, something more parameterized that's actually taking into account the current state of the system, which actually changes over time quite drastically. There are a lot of lessons learned with regard to temporal locality and spatial locality and things like that, but I don't necessarily have to go through all of these individually. We did a similar analysis with the Argonne Argonne Leadership Computing Facility at Argonne National Lab with a mirror system there. So we split between different faults, errors, and failures there, did a similar analysis, and came to some of the similar results, but also some different results. So for instance, Mirror observed a higher failure rate during summertime than during wintertime, which we didn't see at Oak Ridge, and we still don't know exactly why that is. Right. So at Livermore, one problem there is most of the big systems at Livermore, of course, are classified, and we can't really take that data and then just make that public. But we started working at Livermore, looking at clusters and looking at the memory errors, how the memory errors are distributed, and is the distribution actually matching up with anything else. So we do see a spatial correlation of memory errors, and we are still looking at, is that related to room temperature or is that related to something else? Something important to note here is that for all of these systems, especially less with a mirror system at Argonne, but especially with Oak Ridge systems, when we do see high